Ladies and gentlemen, please welcome to the stage Joe Vinciquerra, Senior Director at GE Aerospace, and PJ Maykish, Vice President for Strategy at SCSP.
Good morning, everyone. Thank you so much for spending time and hanging out with what is going to be a really fun panel about AI in action. We're going to talk about a decade of defense innovation at GE Aerospace. And just to set the stage, I want you to think about how aviation innovation has happened in America. Like the Wright brothers in 1903, just trying to figure out how to get 800 plus feet on a beach. 66 years later, the United States was putting human beings on the moon and returning them safely alive in just 66 years. But the history of that innovation happens with people like Joe. And so what we're going to dive into is not only Joe's world and Joe's organization, but in some sense, like how America innovates. And so please welcome Joe Vinciquerra. What we're going to talk about here today is he's the Senior Director at the GE Aerospace Research Center. And I think when you think about great labs in America, you think about our national labs or DARPA or Big Safari, our great companies also have these amazing research companies, and Joe's in charge of GE Aerospaces. So Joe, please, just to get everybody a chance to get to know you, please tell them a little bit about how did you become the director, how did you get into aerospace?
Yeah, absolutely. PJ, first of all, thank you so much for having me. I'm so excited for this conversation.
Yeah, me too.
And on the subject of great research and development labs, I will start by saying that GE Research and Development was the first national industrial research lab in the country. So this year will be 125 years old.
Amazing.
And so I love telling that story.
Amazing.
Yeah, for me, I'm going to take you all the way back to when I was in high school.
Please.
Okay.
Yeah.
In high school, there were two things that mattered to me, and only two things, and neither of them were STEM related. Number one was art. I was a big fan of art and the idea of invention and sort of creating things for the first time. The other thing that I was captivated by and spent all of my free time was with cycling, road biking, if you will. So think Tour de France, things like that. Right up until the last minute, I was going to go to art school and I was going to ride my bike. Those were the two things that I focused on.
We're talking like teenage years.
Yeah, this is like 14, 15, 16.
Okay.
But right up until the end, because 4 out of 5 schools that I applied to were art schools, if you can believe it. But something happened, and I'll date myself, and I'll take you to 1996, because that's when all of this was unfolding. In 1996, two things happened that changed my career trajectory for the rest of my life. Number one, the guidance counselor at the time said, you know what, you're actually okay in math and science, you should think about doing something in that field. Okay, I'll consider it. But the more important thing, the more influential thing that happened was the USA cycling team, the Olympic cycling team, it was the Summer Olympics in '96, they debuted a new bike that they called a super bike. And the super bike was made out of this material called composites. And the way we refer to this material today, colloquially, is carbon fiber. And I saw this article in a magazine around the use of carbon fiber to create these so-called super bikes. And these bikes were like unlike anything I'd ever seen before. They didn't look like bikes. And as I read through how this bike was made, I learned that it was from an aerospace industry technology, that composites were being used in aerospace because they were lighter, they were more durable.
Interesting.
That same year, to bring the story full circle, GE introduced the first all-composite fan blade on the GE90 commercial jet engine. 1996, it entered service.
Nice.
After 20 years of research and development, first beginning with NASA and the government, and then ultimately evolving to one of our most differentiating product technologies. To this day, it's 30 years later, and we're still the only flying aircraft engine with a composite fan blade. So that moment, that culmination of things, changed my trajectory. I went into aerospace engineering.
Amazing.
I studied composite materials. Fast forward, I now have the privilege, as you said in my intro, of leading GE Aerospace's Research and Development Center, where we do work like this every single day.
I think what's like to think about you as an artist, as a kid, and then transitioning that into actual science and technology is fitting for what you do.
It absolutely is.
It's fitting, yeah.
Yes.
It's cool. Like everybody's life happens in chapters, right? It's cool to hear some of yours.
Yes.
I think not everybody in the world knows how long GE has done AI. And so what I want to ask you about, Joe, is just if you could just school us all up on what is the history of AI at GE? And GE split into 3 cool companies, aerospace, health, and energy. going back, like,
Yeah.
what is some cool stories about AI at GE before we talk about the center?
Yeah, so AI is just, it's everywhere right now. It's so accessible to absolutely everybody. You can do things on your phone, you can do things with ChatGPT. Everything we touch and interact with now on a daily basis practically has AI infused in it. So while it feels very new, it's actually not. It's a science that goes back several decades. I've been with GE now for over 21 years, and I can tell you that we've been developing various forms of artificial intelligence, machine learning, probabilistics, et cetera, for a long, long time. Within GE today, deployed in the field, we use AI to optimize our supply chains. We use AI to optimize our maintenance, repair, and overhaul facilities on the commercial side. Certainly for national defense, we have AI infused in everything from our design processes all the way through our maintenance and overhaul centers. So AI is really everywhere. It's infused in our operations. It's infused in our technologies. And there's some really, really cool things behind the scenes that we've done with AI for a long time at the Research Center.
When you started, you did an AI, like you starting at GE, you had an AI materials program?
Yeah, so let me deep dive. So going back 10 years ago, not quite when I started, but sort of mid-technical career, we've used various forms of artificial intelligence. Really, take a step back. When we think artificial intelligence, a lot of times these days we're thinking about things like ChatGPT. We're thinking about learning algorithms on the apps that we use and things of that nature. Those are the things that are impacting our life. It's a very software type thought when we talk about AI. Where we spend quite a bit of time, where we have leveraged AI in the company, and where I have personally worked in AI, is at the intersection of the digital science and the physical science. And so, as an example, to pick up on your question, PJ, about a decade ago, we were beginning to do work on advanced artificial intelligence techniques to accelerate the development of advanced materials. The materials that we use in the aviation industry are extremely complicated to produce. They're extremely complicated to derive. And what we found is AI, like it can be in so many other areas, can be a great accelerator for that. We had a program with DARPA, in fact, about 6 or 7 years ago now, where we were looking to develop a new material system for hypersonic structures, hypersonic vehicle structures. And as you can imagine, these material systems need to sustain extremely high temperatures, they need to be very durable, they need to be manufacturable. So you have a very sort of classic multi-optimization problem. We were able to, in the span of a year, develop over 250 unique material systems that satisfied all of the optimization criteria and physically produce these compositions in our laboratory in upstate New York. And all of that was done in the time that it would have historically only been able to do a dozen or so. And that was because of artificial intelligence.
Amazing.
Yeah.
Amazing.
Yeah.
Why don't you take everybody here to kind of take them into the center now, right? And what's going on at GE Aerospace with AI at the Research Center?
Yep.
It's in upstate New York, right?
Yep.
And tell us what's going on there.
Yeah, so the Research Center is located in upstate New York, about 5 miles from where it was founded in Schenectady, New York, also where GE, the company, was founded, I said, about 125 years ago. We have over 1,000 employees, 3/4 of which are the researchers, the majority of which hold advanced degrees. We have in total the equivalent of 6 football fields of physical laboratory space where we do research across all STEM domains that you can imagine. Over 50 different scientific capabilities are represented by our workforce. With respect to AI and sort of the history of the Research Center, as you said a moment ago, we used to sit within the center of the large conglomerate of the General Electric company. For the history of the company and the history of the Research Center, we focused on applied research and development for the sake of product development and industrial expansion. When I first showed up 21 years ago in the Research Center, we were developing artificial intelligence techniques for image recognition and what we would call today in our sector defect recognition, but we were developing it for healthcare. And we were doing it so that we could more quickly identify images and things that you might see in an X-ray or an ultrasound. That technology was deployed and then later ported over to our aerospace business much of which today is used for manufacturing and quality control. So another example of these long incubation times of things like AI in the research center.
Fantastic.
Yeah.
I think for everybody who's joined this session, at SCSP, we're always thinking about how public-private partnerships really bring the innovation ecosystem together. I have learned, and still have more to learn, there's some really cool examples in happening at this what it was an old American company that's been renewed and modernized, right? And so, Joe, can you just tell everybody a little bit about maybe some historical public-privates?
Yeah.
How does innovation really work at GE with the government, for the nation?
Yeah. I'll give you a couple examples. I mentioned the composite fan blade in sort of my origin story, if you will, right? That was work that began with the government. It began with a partnership with NASA, and then later we recognized the need for that technology, not only for our company, but for our nation, quite honestly. About a decade later, we started research in a different type of composite material we call ceramic matrix composites. Ceramic matrix composites are a composite material, obviously, and they were designed to replace nickel-based superalloys. So these superalloys are a great example of material systems that I said are very difficult to manufacture, very difficult to source, but they're everywhere in our engines and really across the aerospace industry. I actually brought some examples here. And this work actually started with the Department of Energy. Okay, and the query at the time was, can we drive new efficiencies in power-producing gas turbines because efficiency is everything, particularly at the time of the oil crisis.
Yeah.
Fast forward, we later developed a material system for our turbo machinery, but it was predicated on the same work with the Department of Energy and later the Department of Defense. So ceramic matrix composites versus nickel-based superalloy. I have these two components here, and I know it'll be hard for folks to see, so I'll try to describe it. These are called shrouds, and shrouds basically encircle the rotating parts of the hottest part of our engine, the turbine module of the engine. They run very, very hot. There's no hotter location in the engine, and the idea is that the shrouds kind of create the abutment to the rotating blades, and you want to keep those clearances really, really, really tight for efficiency. This is a nickel-based superalloy. This is one segment of a shroud. You can picture a ring of these all the way around the turbine. And if you look at it closely, PJ, you're going to see a bunch of cooling passages. And if you look at the side, you're going to see these very complex drilled patterns that allow for us to cool these materials while we fly them. Very high temperature capable metal still needs to be cooled, otherwise it will melt. That's how hot it gets. I'll let you hold that for a moment. That is a nickel-based superalloy. The ceramic matrix composite is a third the density of what you're holding there and can withstand 500 degrees Fahrenheit more than that alloy. This is twice the size.
It's heavy.
This is twice the size. Take a feel of that. Almost disappears in your hand.
And you don't have any of the cooling shafts.
And there's no cooling holes. They don't need to be cooled because any air that you take out of the engine that's not dedicated to combustion is efficiency loss.
This just feels like any machine made of this would be massively heavy, right?
Right. So ceramic matrix composites is a great story. It started with our relationship with the Department of Energy, later the Department of Defense. These parts are flying today in our commercial products. You'll find ceramic matrix composites in all of our most advanced engine designs, whether it's the next generation adaptive engine for fighter jets or the T901 helicopter engine. We're proliferating CMCs in virtually all of our products today.
If we get these back, can I pass them around?
Yes.
Okay.
Yeah.
Sir, thank you so much. Old, new.
PJ, another example of public-private partnerships is in the area, and this is another area super exciting to me and to our industry, supercomputing. So we have joint activity with the Department of Energy and with Oak Ridge National Lab in the use of supercomputers to run simulations like we've never been able to run simulations before. Department of Energy with the Frontier supercomputer at Oak Ridge is the first exascale supercomputer available on Earth. And there was a solicitation put out for, hey, what are the most complex physical problems that we can throw at the supercomputer for modeling and simulation? Now, I'm not a computer person by background. I'm a materials person, so it took me a while to wrap my head around how powerful is an exascale supercomputer.
And if I could just interrupt for a second, if you haven't been to Oak Ridge to see Frontier, just imagine a stack of GPUs as far as the eye can see, all acting as one.
Yeah.
So it's computers upon computers, 1224, if not more, all acting as one.
Yeah.
So that's what Joe's, just to visualize it.
Yeah, it's exactly right. And it runs 1 quintillion calculations per second. Now, I don't know about you. I didn't know what a quintillion was, okay?
It's hard to visualize it.
So think about this. If every person on Earth did a multiplication problem every second, okay? Multiply a couple of numbers together every second, it would take 4 years to do what Frontier can do in 1 second.
Unbelievable.
That's a quintillion calculations.
Unbelievable.
It is unbelievable. And what we're leveraging that for is simulating extremely complex physical phenomena, mostly around computational fluid dynamics. This is for things like aerodynamic design, acoustics, et cetera, that allows us to almost obviate the need for physical testing. Whereas in the past, we would have to model, test, calibrate, model again, back and forth. We can now run these extremely complex physical problems on Frontier in a matter of orders of magnitude less than what we could do before. So it's really remarkable.
So like public-private at its finest.
Absolutely.
For those who are not in aviation, when the Wright brothers figured out how to fly, there's an argument that they flew sooner than anyone else because they did thought experiments as shortcuts to direct trial or vicarious trials.
Yeah.
So in some sense, you got a quintillion vicarious trialing machine.
That's right. That's right. This literally takes years off of our design cycle.
Yeah.
And I'll take it one step further where we're going next,
Please.
and this is work that we're beginning with other agencies I won't name for now. What does the fusion of supercomputing and AI look like? And we're doing some really, really exciting work at the Research Center right now on that fusion. And so if we can simulate these physical phenomena in orders of magnitude time periods than in the past, imagine what we can do when we layer on top generative AI methods and multi-objective optimization methods. That's another chunk of years coming off what is historically a very long design cycle for things like aircraft engines and other technologies that we care about, not only for our company again, but for national security.
You know, I would love, I've been planning to ask Joe this, and I don't know the answer. I'm really looking forward to it, to just talk about technologies that are exciting to him and his world. Yeah. But since you brought up Frontera, just as a twist, what are some of the hardest problems in aviation for you, that are set before you in the Research Center, that maybe with the combo of AI and supercomputing you can start to take down? Like, what are the big problems?
You know, one of the things, kind of going back to when I was younger and in college, one of the things that I have always retained since my academic career was that the jet engine, today's modern jet engine, and this is true today just as it was 25 years ago, today's modern jet engines are the most engineered mechanical systems on the face of the earth. We get excited about decimal points of efficiency gains when we talk about the next generation of jet engine technology. And when we think about, when we look through that problem from through the lens of national security, we think about incremental advancements in propulsion, agility, efficiency, et cetera, how you continue to improve upon those systems is remarkably challenging. So when we talk about Frontier and the ability to simulate in ways that we never have been able to before, we have accelerated the design and the exploration process. Same thing with the materials examples. We can do so much more in such a shorter amount of time that we've really kind of opened up a new step change in capability for, again, not only our products, but for the warfighter, because we have these accelerators now.
So cool.
Yeah.
Yeah. So if you could please share, Joe, like what the tech that's in the center, let's start there. I'd like to work out a step, the tech you're shooting for, and then eventually the tech you see around your environment that's not even in the center yet. But just starting the center, like what wakes you up every day? What excites you, sort of like the tech that's in the center?
Yeah. So look, there's more than I can list in one place. I mean, hypersonics is a fascinating field, and we're deeply invested in hypersonics. In fact, we just released news that we're going to be making additional infrastructure investments to do more physical testing of hypersonic technology. Lots of our development timelines are on the order of 20 years. That's part of our industry. It's also part of the incubation for R&D. 20 years ago, I started, we were working on a new type of combustion system. We called, at the time, pulse detonation. Today, we've evolved that to rotating detonation.
Yeah.
So last year, we demonstrated a subscale demonstration of a rotating detonation combustion
Could you
engine.
explain pulse and rotating det just to break it down to somebody who doesn't feel the difference?
Yeah, it's a great point. So if you think about typical combustion, you can imagine sort of holding a pilot light in a combustor and then passing air and fuel through that pilot light and burning that air and fuel in a controlled way that then powers the rest of the machine.
Yeah.
It's that sort of steady state combustion, if you will. Rotating detonation is like holding a candle in a tornado. It's having a single spark combustion happening that sort of runs around the annulus of the combustor at incredible velocities. And you might ask, well, like, what does that mean in real life? Like, why do we care? It actually allows us to combust in a much shorter axial space on an engine. And why that's important is because in things like ramjet applications, you want to be able to conserve as much axial space in the propulsor as possible. And the only way to do that is to fundamentally change how you do combustion. And so we demonstrated that phenomena a year ago. We went from concept to subscale demonstration in less than a year. And we're now headed toward full-scale demonstration of that technology within GE Aerospace. So that's exciting.
It is exciting.
When I look at the future, we'll stick with AI, but I'm going to add a twist to it. The intersection of AI and manufacturing is what I think is coming down the pike for us. I know there's a lot of activity in industry on that space right now, but for us, you know, back to jet engines being the most engineered mechanical system on Earth, producing jet engines at scale and at the speeds that are necessary by today's climate, that requires new technology. And when we start looking at layering AI on top of logistics, supply chain, the manufacturing industrial base, having flexibility and diversity in our manufacturing centers, in our depots, that to me is a step change that's coming. I'm very, very interested in how all of that comes together, and we're frankly inside the company just beginning to get our footing on that. And so that's exciting to me in terms of a future perspective.
Fantastic.
Yeah.
Really cool. I mean, for those who are not feeling this yet, this hypersonic technology that's being worked on could someday, like in your lifetime, result in hypersonic passenger travel.
That's
let
right.
alone like hypersonic technologies for the military. But we're talking about like US to Europe in 90 minutes or something like this, right?
That's right.
It's exciting to think about.
Absolutely.
Really. The material stuff which you grew up with is actually mind-boggling. Like we are now with AI making materials that no human has ever made before, conceived of before, like optimizing. So if you were to look now, having described both the public-private with Frontier, amazing, material science, literally optimizing for hypersonic, rotating detonation engines, amazing analogy.
Yeah.
What's the tech that's out here that you think, like, just in your lifetime excites you that you could combine?
Yeah, you know, look, there's a great need as we look at future aircraft, future mobility for more electric power. And you can't avoid that as a innovation wave that's coming. And you might say it's already here, arguably maybe, but one thing's for sure, going forward, we're going to need to be able to produce more electric power, whether you're flying hybrid electric, whether you're fully electric, or whether you just need the power for the mission.
Right.
So I think there's technologies happening everywhere around how do you go from today's state of the art to a more electric power aircraft environment. We're doing quite a bit there. Also, another great example of public-private partnerships. A lot of work with the Department of Energy, a lot of work with the Department of Defense. But also, you know, whether you're on the civilian side or you're on the military side, it's unavoidable that we're going to have to be more electric as we go forward. Not just for sustainability purposes, but because the missions require it. So that's something that's happening kind of in our periphery. In addition to alternative combustion fuel systems, I mean, we look at things like hydrogen as an example for a potential fuel source going forward. So there's a lot of stuff in what we call sort of the N+2. It's not the next gen, but it's the generation after that. And those are some of the things that we're looking at very intensely inside GE Aerospace.
You know, for everybody to feel this, if GE were to break out in hydrogen-powered flight, the exhaust of a hydrogen engine is water vapor.
That's right. Nothing but water.
Yeah, literally. So if you want to think about what makes the world move to carbon neutral, it's really not carbon sinks, it's changing aviation.
Right.
And that's awesome that that's an N2 for you.
Yes.
It really is, yeah.
Yep.
So since we're talking about the research center, I think it would be fun for everybody to feel here, like, what is, as we close, you know, and I'd love to get some final thoughts from you. How many people are there? You mentioned the expertise is there, but just how GE is a place where talent, you're hiring talent, you're building talent.
Yeah.
You're an example of that. Like, you grew up there, and how many people are there? What are the kinds of specialties that are there?
Yeah. So let me start by saying, you know, the research center has, as I said, 125-year history in the company. It was the nation's first industrial research lab.
Amazing.
It is. It's an absolute honor to have the responsibility of now leading it.
I think of Bell when you say that.
Exactly. Exactly. And through every chapter of the General Electric company, the research center has been a constant. So that's number one. Number two is we are an innovation company. The industry is interesting because it's a long cycle industry. Safety is always the number one priority in all that we do. Development timelines, as you have gleaned from some of the examples I've given you, are typically on the order of a couple of decades or more. But at the same time, technology is moving at light speed in all these other sectors, like AI, for example. So the research center is really an accelerator of innovation at the center of the GE Aerospace company now. And as you mentioned at the outset, you know, we've separated out the other parts of old GE. We have a GE Healthcare, separate company, a GE Energy business called Vernova, separate company. What remains is GE Aerospace. For 100 plus of those 125 years, we have been innovating these firsts for the aerospace business, what we call aerospace today. Whether it's the composite fan blade, whether it's the CMC material system, supercomputing and the numerical methods needed to actually exercise frontier the way that we do. Or we didn't even talk about additive manufacturing, metal 3D printed parts. All of those examples had roots in the research center, every single one of them. And there's many that I'm not mentioning here. So our workforce, as I said, is about 1,000 employees. All told, GE Aerospace, I'll give you last year's number, we did $2.7 billion with a B dollars of R&D, and a significant amount of that happens at the research center in upstate New York. In terms of capabilities, it's literally every STEM field you can imagine, from chemistry to metallurgy to computer science to mechanical engineering, aerothermal sciences, you name it. We purposely seek out and attract very deep, innovative thinkers who have a desire to apply their knowledge for not only product development, but for our national position.
Amazing.
So, yeah. It's a special place.
So just to give everybody a sense, if you feel it, when you think of an organization like DARPA, it's like all of DARPA, roughly 4.7 billion. So 2.7 billion in just a company's R&D is a massive number.
That's right.
ARPA-H is like $1 billion, a little much less than that. Amazing organization. AFWorks about $1 billion. So that's it. I didn't know the number. It's a big number.
It's a big number.
Really, really cool.
Yeah.
So just to close this, you know, I want to say, like, I was career Air Force for 24 years. When you go through your career, you realize that everything we do is the result of thousands of people who care, thousands of people who wake up every day to do what you do.
Yeah.
Really, like 1,000 American Joes that just come build everything we have, you know, build our future. And like, power is hollow unless you have things like this, you know. So I just want to say thank you, because I've really like realized over time that we are you, you know what I mean? We are you. And so just as we close to this audience, I want to thank you all so much for being with us to think about AI intersecting with aerospace. Nobody finer to talk about it than with you, Joe.
Thank you.
Just any final thoughts for the team here about the subject of the panel?
I'll pick up on something you said at the end there. I'll throw out a statistic because I think even you were surprised by it, that 2/3 out of all of our military helicopter and fighter jets are powered by GE Aerospace technology.
Amazing.
It is an awesome responsibility that we carry and truly an honor. So we have the privilege of bringing science and technology and innovation to serving that mission, and that's what wakes us up every day, and we just keep looking forward to doing it day after day.
Yeah, that's awesome. I want to thank you for it. Ladies and gentlemen, can I please have a round of applause for Joe and GE Aero? Thank you so much.
Thank you.
Thank you, Joe.
Thank you.
Thank you so much, Joe.
My pleasure.
Appreciate
Thank
it.
you.